Hello guys, welcome back to my channel, and in this video I would like to do an infinite sum but using what will turn out to eventually be a very elegant method. So let's get started and you can see for yourself. So okay, we have the infinite sum, let's call it S, which is defined as the sum from say index j equals 2 to infinity of 1 over 2 to the j minus 2th power times the tangent of pi over 2 to the jth power. And now what I can do is use some properties of exponents, right? This is sum from j equals 2 to infinity of 1 over 2 to the j times 2 to the minus 2 power and the tangent of pi over 2 to the j. And I can take this on top, so I'll have 2 squared in the numerator with basically a positive power, which is nothing but 4. So 4 times the sum from j equals to infinity of 1 over 2 to the j times the inverse the regular tangent of pi over 2 to the j. Okay, notice that this exponent term is present outside as well as inside over here. And now here comes the most important part of this video, or what I call the clever observation. I mean, it's based on this observation that this entire method becomes a very elegant solution. So notice that, well, what is the antiderivative of the tangent? Negative natural log of cosine of that variable, right? So if I have negative derivative with respect to x of natural log of cosine of x divided by 2 to the jth power, if I basically differentiate this, what am I going to get? I'm going to get minus, well, this entire thing is just the derivative of the tangent. So tangent of this inner thing, x over 2 to the j, and we have to use the chain rule basically. So we have the derivative of the inside argument, which is x over 2 to the jth power. This becomes basically 1 over 2 to the j times the tangent of x over 2 to the j. This is basically what this expression evaluates to. And if in place of x later on we plug in pi, we get 1 over 2 to the jth power times the tangent of pi over 2 to the j. So we can write this as taking the derivative with respect to x, and then after taking the derivative plug in pi. And notice what this thing is. This is just a summand, this part, right? So why not express this this summand that we have here in terms of this derivative with respect to x, and then plugging in x equals pi after taking the derivative? Well, it's because of the reason that we obtain a natural log, and logs in general behave extremely well with sums. And wait, if you're not convinced, let me just write this in terms of a derivative, and then you'll know. So as discussed, we can write this as minus 4 times the sum from j equals 2 to infinity of the derivative with respect to x of the natural log of cosine of x over 2 to the jth power, that's evaluated at x equals pi. So after you take the derivative, you plug in pi. That's what this is saying. And now sum of a derivative is the derivative of the sum. Basic sum property, basic addition property of derivatives. So we have minus 4 times the derivative with respect to x of the sum from j equals 2 to infinity of the natural log of cosine of x over 2 to the jth power evaluated at x equals pi. And why I said logs were really behaved really well with sums is because if you sum up logs, say log of any base plus same base log, if you do that, this is just going to be log of those common bases. Here it's e, natural log, a times b times whatever was added. So we can convert this sum into a product. So basically, if we have a sum of logs, we can write this as log of a product. So that's why logs behave really well, because then you can express the sum of logs as log of a product of arguments, and that's going to be really really helpful for us. You're going to see in a bit. So we can write this as minus 4 times the derivative with respect to x of, well, natural log of product from j equals 2 to infinity of cosine of x over 2 to the jth power, then again evaluated at x equals pi, the entire derivative. So now look inside the log, look inside the argument over here. This is an infinite product problem, right? A separate one, almost seems unconnected to what we had in the start in infinite sum. So what I'm going to do is I'm going to treat it specially. I'm going to use a fresh page. See you then. Okay, we have this infinite product basically. If you want some perspective, let's write down a few terms. So we have cosine of when j equals 2, or 2 squared is 4. So x over 4 times, because it's an infinite product, cosine of 2 to the third power, which is 8, x over 8. And that goes on till infinity basically. So now, if you might recall, we had done a similar series in one of my infinite series videos. You can probably added a card about now. So in that we have to convert it. We have to solve this in infinite product. We have to convert this into a telescoping series. And to do that, I had said if it's an infinite sum, you convert consecutive terms into its inverse operation. So if it's an infinite sum, then you write consecutive terms as a difference, because inverse operation of addition is subtraction. So if you write them as a difference, if you manage to write them as a difference, you can somehow manage to cut out consecutive terms and you'll get a telescoping series. Or if you have an infinite product, you can write consecutive terms, if you can manage to write consecutive terms as a quotient, then in the entire infinite multiplication, consecutive terms may get cut because they're expressed as a quotient, which is an inverse operation of multiplication. So since we have an infinite product, can we convert consecutive terms in terms of quotients? So if you recall this, I mean this we had a really identical series for in that video. So please watch that video. We had used double angle formulas, and in this case we are going to use the sine double angle formula. Sine of 2x is 2 times sine of x times cosine of x. So we can write cosine x as sine of 2x divided by 2 times sine of x. So if when we do that, our infinite product from j equals 2 to infinity of cosine of x over 2 to the j can now be written as sine of, well, the first term is x over 4. So first 2 times of this x over 2 divided by 2 times sine of the original thing x over 4 times, because it's an infinite product, sine of 2 times this is x over 4 divided by 2 times sine of the original quantity, which is x over 8. And we can do that this until infinity, and say the last term is sine of x over 2 to the j minus 1, because it's going to be twice of x over 2 to the j divided by 2 times sine of x over 2 to the j. And since j is going to be a last term, and recall that we had an infinite product, infinity was our upper bound, we can take the limit as this last last representative term with an index of j that goes to infinity, because it's an infinite product. So now notice the best part here. These consecutive terms are just going to cancel out, because now it's a telescoping series. It's a full-fledged telescoping series. So x by 4 goes with x by 4. This, well, x by 8 is going to cancel with this numerator of the next term. And then this term that we have over here is going to cancel with the previous term. So all we are left with is this first term and then this trailing term. So we can write this as sine of x over 2 outside the limit, because it does not depend on the last um, term index, times limit as j goes to infinity of sine of x over 2 to the j in the denominator basically. So as I said, we have a sine of x over 2 to the j in the denominator, but remember that we are also multiplying 2 j times, because the last term, if we assume j and we take the limit as j goes to infinity, then we're multiplying 2 basically with itself j times. So this is going to be 2 to the j, accounting for all these different 2's that we have. And how do we evaluate this limit? Because as j goes to infinity, this will go to infinity. This, the denominator will go to infinity, and then the entire argument of this sign will go to 0. So we have 1 over infinity times 0 situation, but we still can't use L'Hopital's rule. We need something like 0 over 0 or infinity over infinity for L'Hopital's rule. 0 over 0 or infinity over infinity kind of situation for L'Hopital's rule. So what I'm going to do is sine of x over 2 is basically the free term. We can write limit as j goes to infinity. I'm just going to put this 2 to the j in the numerator, making a negative power 2 to the negative j divided by sine of x over 2 to the j. And now notice what situation we have. So as j goes to infinity, this exponential term will decay to 0. We have 0, and then again in the denominator we have 0. So we have a 0 over 0 situation. Now we can officially apply L'Hopital's rule. Basically differentiating the numerator and denominator by this variable of the limit. So differentiating with respect to j, because there are two variables in the sign, so I don't want to confuse you. That's why I said differentiating with respect to j. So we limit as j goes to infinity. Now you differentiate. We have 2 to the minus j times natural log of 2 basically. That's how you differentiate an exponential with a negative sign for the negative j. And in the denominator we have a cosine of x over 2 to the j times x as it is because it's a constant with respect to j. And we again have to this exponential term which is 2 to the minus j if we just bring it in the numerator of the argument, which is going to be again like the numerator minus 2 to the minus j times natural log of 2. So well, the entire numerator will just cancel out with this. So we are left with the limit sine of x over to outside times the limit as j goes to infinity of 1 over, well this x remains, cosine of x over 2 to the jth power. So as j goes to infinity, the denominator going to infinity will make the entire argument go to 0. Cosine of 0 is 1, so this entire term goes to 1. Nice. So all we're left with, this entire limit just evaluates to 1. We just have the sine of x over 2 that was outside divided by this x that was unaffected by the limit in j. So that was basically inside the log. This all was happening inside the log, right? The product that we had, infinite product that we had was inside the log. So let's go back and substitute this inside the natural log expression. So let's recall the equation for s. S was equal to basically minus 4 times the derivative with respect to x of natural log of basically product from j equal to infinity of cosine of x over 2 to the j and evaluated at x equals pi. And this all evaluates to minus 4 times derivative with respect to x of natural log of, now we know this term, right? We just calculated it on the previous page. That's natural log of sine of x over 2 divided by x, and you evaluate the derivative at pi, x equals pi. So I'm going to take the suck in the negative and then flip the argument by log property. So we have 4 times derivative with respect to x of natural log of x over sine of x over 2, and again evaluated at x equals pi. So we can just use some log properties before calculating the derivative. We have derivative with respect to x of, we can write a natural log of a quotient as difference of two different natural logs. So the natural log of x minus natural log of sine of x over 2. Again evaluated at x equals pi. So this is basically going to turn out to be then derivative with respect to x of natural log of x is just 1 over x minus 4 times, this is going to be sine of x over 2 and cosine of x over 2, and we have to divide by half also by the chain, for the chain rule, and all of this is essentially evaluated at x equals pi. So now plug in pi here, you have 4 over pi, and then if you plug in pi, you have 4 times cosine of pi over 2 divided by 2 times sine of pi over 2. Sine of pi over 2 is 1. Fair enough, no problem in the denominator. But the cosine of pi over 2 is 0. So 0 over any stuff we don't care, because all of this is just going to go to 0. So all we are left with, and what is all this equal to? S. S is nothing but 4 over pi. Isn't that really fabulous? I mean, no one was expecting the pi, right? I mean, we had a pi in the original sum, but again, pi fails to not surprise us. Now, if you want to write just everything down, just for old times' sake, for drawing a conclusion, we had a sum S from j equals 2 to infinity, an infinite sum basically, of 1 over 2 to the j minus 2 times the tangent of pi over 2 to the j power, and all of this using a very clever observation of obtaining natural logs inside a derivative, and then using the good behavior of natural logs on sums to get products inside arguments, and then making the products to telescope, and then reducing everything using L'Hopital's rule to a final value, and then plugging in the point where we are calculating the derivative, we get 4 over pi. So that there was a lot of stuff we did, and it was a elegant solution, truly, if you ask me. One of the most elegant solutions we've come across so far when we're calculating our infinite series. So anyways, I hope you really like this video, guys. That's it. Hey, so please like, share, and subscribe to my channel. Recommend me to your friends, mathophiles, fellow mathematicians, anybody who wants to learn something new, is bored during lockdown, or anybody. I just want to grow. I want more subscribers. You can follow me on Instagram, gamma_digamma. In the meantime, stay home, stay safe, have a great day, and peace out.